let's talk about natural numbers, integers. And we have these operations we can do, okay? These operations were known by people. Subtraction, minus, multiplication, division. So if we add two natural numbers, then we get natural numbers, right? So this is true. If we add two natural numbers, then we get a natural number. That's true. If we add two integers, we get an integer, right? If we subtract two natural numbers, we don't get natural numbers, right? If we multiply two natural numbers, we get a natural number, but this is not true. Great. Now for z. For z, if we add two integers, we get an integer. If we add two, subtract two integers, we get an integer. If we multiply two integers, we get an integer, but this is not true. So somehow down the line of history of mathematics, this idea of why, like, what kind of numbers made this, like, dividing two kind of numbers give the same type of number comes, and that's why rational numbers and fractions came. So people ask this simple question that, is there a number x such that which when multiplied by y is an integer gives, you understand here, whatever the y you're giving here, y is a natural number, okay? Here whatever y you're giving, it's an integer, because you have updated the system of your arsenal of numbers. So is there a number x such that which when added to y, which when multiplied to y gives 1? So when you will learn, probably you've learned mathematics in your college, or probably so these are called identity elements, okay? You will see mathematicians have, this is multiplicative identity, this is additive identity. And these identity elements are very interesting because that makes this, that's where this is a story of that has been built over the past years. But these are real life problems that people have question, because they ask that, okay, I want one cake of size, of this much size, of this much gram, and I want to distribute among my three sons and two daughters, okay? So how much should each of those amounts be? So that's where the ideas came, okay? This were natural problems, because after the death of the parents, their children inherited the land, and they need to distribute over the, they measure the land and they need to distribute the land, right? So how do we do it? That's where they discovered the idea of fractions. Next time when you teach about numbers, or when you share about numbers to your juniors, to your sisters, to your brothers or cousins, or whoever you're teaching and sharing, please tell these aspects, okay? That will make them interesting. Yeah, you will play an important role in better education of the country. So, and that's where the whole idea of rational numbers came in. Q. So rational numbers are the set of all those a by b such that a belongs to z and b belongs to natural numbers. So we did this last day, unique definition, a by b. Also you can divide by z and z non-zero z, where a and b are co-prime, but let's do it by this method. The interesting aspect is that the q, what you have seen, if you add two q's, it's q. If you add two rational numbers, it's rational. If you subtract, if you multiply, if you divide, all of them are rational numbers. If you multiply by non-zero, divide by non-zero. And that's why we'll see this is something interesting. This is called in mathematics, in modern mathematics, called ring. I think this is called a monoid. I'm not sure. Just have to check. If you're from a mathematics background, probably you will know this. And this is called a field. A field is a set of numbers which which when you add it, divide, and whatever you do, like whatever these operations you do, it always turns out to be inside that set. This is called closed property. And this is very interesting because this is how people have all these ideas are nothing but checking the closeness property, because this plus, minus, subtraction, plus, minus, division and multiplication are all real life objects, okay, that human beings saw and developed, and that came as a natural existence in mathematical abstract mathematics. So they define like this. These are called binary operations in mathematical binary operations. Yeah. But it has developed right now to more abstract operations. Binary operations are different, but the basic idea is this: that this is how the thing were developed. So people were really happy with this thing, and they were, they were having parties and great time were going on until Pythagoras came into the picture. And Pythagoras came and it changed everything. That and Pythagoras came, and you see, you remember? Do you know when Pythagoras was there? Is it in the BC or AC? Do you remember? Yeah, Pythagoras from AC or BC, before Christ or after Christ? It was much before Christ, 500 years ago before Christ. Okay, so all this was developed, almost 2,000 years ago. It's like a lot of time ago. So Pythagoras came in and he told. So how do you know how Pythagoras theorem was developed? How Pythagoras theorem, how history of Pythagoras theorem? It's very simple. Okay, so previously, I think it was some tribal community. I think they used to measure. So they used to count the numbers, like these knots on strings. Okay, like this. Like we use this difference, this points to count the numbers in our childhood or the fingers. Similarly, they used to use these knots. Okay, as an advanced technology. And they observed that that if they did this and there was like string like this and it did another string like this, what they observed was uh, that this length, I'm sorry, yeah, I did a mistake. So observe that this length is 5. So it's 3 square plus 4 square. Like essentially it came out of measuring the fields. Okay, the field. So they wanted to understand that are there A and B such that a plus b whole square, this happens. So they discovered that right angle this, they came out of the idea of Pythagorean triplets. Okay, that came first. And yeah, although this existed much before in Indian history, if you see, the Pythagorean triplets exist much before in the Rig Vedas. Okay, in Indian culture, in the culture of the land, and it can be found in Vedas because they formed yagnas. Okay, yagnas, if you remember, yagnas, which in Bengali is called yoggo, yagya. And the yaggic, the place where they did the yaggic structure, that were made of like squares and all these things like this. I will try to show it to you. Probably I will send a picture to you. Yagna, uh, with Pythagorean, with right angles, from Vedic age. I'll probably find. I mean, you can understand from the intensity of this whole yagna. I mean, um, yagna. I'm not finding that, but you can search about that. I will probably send you the book. But you can understand the complex geometry of the entire, um, the this one system is called mandala. I have shared in the group. You can check that probably later on. That how Indians and how our Hindu, the Vedic people were so mathematically talented, and it's beyond the perception of our age. So all these were known before, like in the Vedic age. Okay, thousands and thousands of years ago. So much before before Christ and all these people came up. And that has been recorded in Indian literature. In Indian Vedic literature, you should go about and read about that. Okay, it's very, very important if you want to. Okay, so coming back to this, so coming back to the now current situation, that uh, rational numbers were discovered, and people were, this, then Pythagoras came in, and then Pythagoras, from Pythagoras theorem, it's very natural to ask that what's the length of this. And they found it to be root 2. Root 2 is nothing but, sum of two, square root of these two numbers. How was square root defined? It's like x, something which is multiplied by itself that gives 2. Okay. And they proved this root 2 is not rational. We have proved this a lot of multiple times. Not rational. They proved it. Like they cannot be expressed in p by q format. So they were very surprised. They understood, oh my god. So there is another, another real number type, another number. This number, this length, which is never be rational. Like what kind of number it is? We need that length, right? They need that length to measure all these things. So what kind of number it is? That's a much more interesting problem. Like what is this number? Where does this come from? What's the property of it? And this intrigued the mathematician and all those scholars to the fullest. Where did this come from? And they studied for years and years and years, and it's hard. And they found, so, and then they came up with this definition, okay, that, see, understand that this is a subset of this, all these are subset of this. So therefore they understood that there are two types of numbers. One is rational number, and something that is not a rational number is called an irrational number. That is not rational, that is irrational. So understand, if this is a real number line, therefore, and if you can plot this small numbers, let's say rational, there are certain holes. So you can find as the holes are nothing but the irrational numbers. Okay, the holes are nothing but the irrational numbers. Okay, do you understand? So therefore the next natural question is that how are the rational numbers and the irrational numbers related to each other? So understand that from natural numbers we got the idea of zero, and we got the idea of negation, negative numbers, subtraction to go to z, and from z we got the idea of division to go to q. See, the subtraction, like multiplication and addition was mostly there in all of them, but the subtraction and division make the difference. Okay, that's why the inverse operation made the difference. So the next question is that we went to real numbers. We understood that there are some numbers more than rational numbers, and we have defined all those numbers to be in two formats, either rational numbers or irrational numbers. Okay, we divide that. So therefore the next step is a real number. So real numbers is therefore rational numbers union irrational numbers, and they are disjoint because that's how it's defined. Okay, So how, what is the like, how can we jump from this how can we use these rational numbers and take as a building block to build the real numbers? So that was the question they, they really thought. And the next part of the lecture, the next part of the discussion will be focused on this. How did they do so? And this story is really intriguing, and you will see everything coming up so naturally in existence. So did you understand it? Whatever story I have shared to you till this point of time, guys? Thank you. Great. If you have doubts, you can ask me. Okay. So the question is that how did they do it? So the next part is that, yes, so as I have told that this from 1 and 1 they discovered like something called root 2 Sriya, okay? And they understood that root 2 was not rational. That means they intrigued that that made them think that, oh, there are some real number lines like this. So if I add these two numbers and there's another line like this, which is not a rational number. That means it's something outside whatever we understand from their perspective. They think that the world was made up of rational numbers, irrational numbers, and they found a line and they proved that it cannot be a rational number mathematically. So it's some kind of other numbers, right? So therefore they define that, okay, let's divide the real numbers into two halves. All the numbers that exist in the world into two halves that we can measure by length. Okay, so they can take a scale and they can measure all the numbers are divided into two halves, one that is rational and one that is not rational. And they define those rational numbers like root 2 and others, which they don't know what are rational numbers, what are those numbers, by irrational numbers. Did you understand? That's why you don't even know till this point of time is pi to the power e rational or irrational. So it's not stable. There are conjectures. If e is rational or e, I think e is done. But if pi or others numbers like that is Euler's constant, rational or irrational. So therefore, people even don't know which are rational, irrational. So till this point of time also. So therefore, this natural segregation happened because they were not being able to understand the whole thing. So they divided it into two halves. Did it make it clear, Surya? Okay, great, super. So okay, the next part of the discussion will be based on how did they do it. Super. It's a nice story. I like it. How did they do so? That's the fun part, because that you will see how these things came into the picture. Okay, let me have some water, please. Okay. So so we have already discussed about how. So we have already discussed about how real numbers are described as decimal numbers, right? In the last class. So I'm giving you a very basic idea. So I'm now coming back to the the modern times, not going back to that time in the BCs, and I'm thinking about how it's happening exactly. What's the basic idea? It's because I cannot tell the entire history in the step by step format because it's time consuming. So as you can understand, so I will just ask two questions that therefore, and I mean this is a two basic questions. So what we will do is that so once we try to express in decimal format, numbers in decimal format, um, and that's where the the basic idea of series comes up. That whole idea of series and sequences comes up. So, but that's a different issue. But essentially, there are two questions. So if we have um, a rational number, let's say q, and if we have a irrational number, let's say I1, then you can always find a rational number before and after that, and you can always find an irrational number before and after that, that q, that rational number. And this is a very interesting property because we'll see why this is interesting. This is the structure of how rational numbers and irrational numbers are related to each other, and that will lead to the different concepts out there. So therefore, to be very precise, for any real number, if you take any real number, any number, then you will always find a rational number and irrational before that, because for both of them it's true, right? So this is the basic idea. For any real number, you can find always a rational number and irrational number before that. And the proof, the basic idea comes from, I think Ronit has shared his answer in the group while I asked that question, that any decimal number, let's say you find any decimal number. So first of all, how do rational numbers look like? So if you see rational numbers, let's say 2 by 3 in decimal format, if you take on that multiple thing, it's a multiple type, it either looks like something it goes on recurring, not recurring, let's say it's, I think it's 0.6666, something like this. So essentially it's something like this, a1 a2 dot dot dot. So any rational number is of the format. You can prove this using basic mathematics. Is of the format, some integer here, then decimal point, and then you will get some numbers like a1 a2 ak, and then a certain thing, a chunk will come, which chunk will keep on repeating. So any rational numbers can be represented in this format, if and only if. So if and only if condition, and you can prove it mathematically. It's a number theory problem, basic problem. So therefore, any number that is not in the format of this is An irrational number.